Hey there! In this video we're going to talk about solving second-order linear differential equations that are not homogeneous. Okay, in the previous videos we talked about the homogeneous case. This time we're going to let that function on the right-hand side be non-zero and see what we can do. Okay, so let's take a look. Before I show you this theorem, let me go up. Let me remind you of a theorem we had from the last section. We had this theorem that guaranteed existence and uniqueness. And it said that if we have the homogeneous equation with any initial conditions, we will have a unique solution. All we need to do is know that these functions p and q are continuous on the interval that we're looking at. So in this case, the interval, they just called it a to b. So if we have continuous functions on an interval, any set of initial conditions will give us a unique solution to that differential equation. What is the case when this is not a zero? What if that's some non-zero function? All right, well, we have a theorem for that, and it's essentially the same theorem, right? All we need to know is that f is continuous. If f is a continuous function on that interval, then again, we have a unique solution. So, important theorem right off the bat. The next important theorem I want to talk about is theorem 5.3.2. This theorem tells us how to get the most general solution possible to our differential equation. Okay, let's read what it says. So if p, q, and f are continuous, let yp be a particular solution of this differential equation. What does that mean? It's just any solution. Particular solution just means it's any solution you happen to have found. Okay, so fine, we have some solution. Now you might say, well, wait a minute, we're done, right? Well, no, because just because you found some solution doesn't mean you now know what every solution looks like. What we want to do is we want to write down what every possible solution could possibly look like. All right, so that's why there's more to this story. It says, let y1 and y2 be a fundamental set of solutions of the complementary equation. Same equation, but with a zero on the right-hand side. Then y is a solution if and only if it can be written as a sum of the particular solution and a linear combination of our fundamental set of complementary solutions. Okay, so this is how you write down any solution. Take any particular solution, find two linearly independent complementary solutions, and then make this combination. Take the particular plus any linear combination of those solutions, and you have every possible solution that you could ever find. Okay, that's what this theorem is giving us. What I'd like to do is take a moment to prove this theorem. Okay, so what we have to do is prove two different directions here. We need to prove that if y is a solution, then it can be written in this form. And then also we want to prove that if it can be written in this form, then it's a solution. Okay? Let's do the second thing first. Okay? So claim. Claim 1. If y equals the particular solution plus a linear combination of those two guys, and these are linearly independent solutions of the complementary equation, which gives us a fundamental set of solutions. If you write it like this, then y solves the differential equation, which we're calling 5.3.3, this guy. So let's make sure it works. Okay, well, how do I know that something solves this? Well, when I plug it in, it gives me f. Or if I plug it on the left-hand side, I should get f as the answer, right? So let's check it. So we need to compute two derivatives of y, one derivative of y, and then we already have y. Okay, so let's compute those. Okay, so two derivatives of y. I'm just going to take two derivatives of each one of these functions. Oh, two derivatives. I also need to have the one derivative, all right? And now when I plug this stuff in to 5.3.3, I should get f. Okay, so I'm going to have y double prime. All right, so that's this stuff, okay? Y double prime is going to be yp double prime plus c1 y1 double prime plus c2 y2 double prime, okay? Plus p times y prime, okay? Let's write it down here. P times y prime, that's this. Okay, what else do we have? Plus q times y. All right. Well, what's y? It's just this, right? Just this stuff. Q times that. Now this is all supposed to give me f somehow. Take a moment, pause the video, see if you can see how this becomes f. All right. So pause the video. I'll meet you back here. All right. 3, 2, 1. Okay. Did you figure it out? Let's see. What you should do here is group all the yp's, all the y1s, and all the y2s. Okay? So let's group all the yp's. So if I do that, I get that. Now let's group all the y1s. Now notice they all have a constant c1 multiplied by them, so I can just pull that out. And what's left over? I get a y1 double prime plus p times y1 prime plus q times y1. Okay, and then do the same thing with the y2s. They all have a c2 in front of them, which you can factor out. Okay. If you didn't get it before, feel free to pause the video and see if you can get it now. Right? What's this? This is the particular solution plugged into the left-hand side of our differential equation. But as the particular solution, it is a solution, so it solves it. So that means that's equal to f. Right? So this thing right here is f. Plus c1 times this thing. But remember, y1 is a complementary solution. It's the thing that when you plug it into the differential equation, you get 0. And c2 times, well, y2 is also a complementary solution, so it also gives you 0 when you plug it in. And so when the smoke clears here, we get f, which is what we wanted to get. We proved that when you plug this guy into this differential equation, on the left-hand side, you get f. And so it solves it. All right, so we have proven claim 1. That's 1/2 of the theorem. If we're of this form, then you're a solution. All right, now let's go the other way. If it's a solution, then it has to be in this form. How do we prove that? Okay, so claim 2. If y solves 5.3.3, then y must be expressible like this. So in other words, there exist constants c1 and c2 and a particular solution and these guys, right? So that y can be written as this, okay? And I really, to be more explicit, I should say where, and then write down what all these things mean, right? But we know what they mean from the context of the theorem, okay? Okay, so we have y, and we know it solves this, okay? Okay, well, we also know that yp solves this. What happens if I take y minus yp? So consider the function y minus yp. What does that solve? Go ahead and pause the video, think about this. What does this function solve? Okay. Okay, 3, 2, 1. Did you get it? Yeah, when you plug this in, if you go ahead and compute its derivatives and plug it in, you get not f, you get 0, right? It makes sense because y solves this, so it's going to give me f, and yp solves it, it gives me f. And because this is linear, I end up with f minus f, and I get 0. So these actually solve, this guy actually solves the complementary equation. All right, so there's a little bit of work here. You should work it out on your own. So blah blah blah. It can be shown that I'll just say it's easy to see that y minus yp solves the complementary equation. Okay. Now, what can we do with this? Well, remember from the previous videos, the previous chapters, if something solves the complementary equation, then we know it can be written in this form. That's what a fundamental set is. It's a set of functions so that any solution can be written as a linear combination of them. Right? So because it solves the complementary equation, and because y1 and y2 are a fundamental set, so because y1 and y2 form a fundamental set, for the complementary equation, we know that this guy can be written as a linear combination of them. C1 times y1 plus C2 times y2 for some constant C1 and C2. We know those constants exist. And I think we have it now, because now all I have to do is add yp to both sides. So therefore, do we put an e at the end of therefore? I never remember. We add yp to both sides. Yeah, one's the old English version where you do put the letter. I mean, I don't remember which is which anymore. Whenever I'm writing like this in video, nothing looks right anymore anyway. So there we go, right? Therefore, we can write it in that form. And that was what we were trying to prove. So, proven. Okay. Okay, so let's do an example. Okay, we are going to solve this differential equation. We're first going to find the most general solution so that any initial condition, we can find the constants that'll solve that. And then we're going to look at an initial value problem and find the value of the constants that give us the solution that satisfies these conditions. Okay, so how do we get started? Well, what did the theorem tell us? The theorem told us that if we could find a particular solution, right, let's go look back at the theorem. If you can find a particular solution and two independent complementary solutions, then the most general solution looks like this. So this is what we're looking for. We're trying to find the particular solution, and then we'll try to find our complementary solution, and we'll just put them together like this. Okay? What's a particular solution? We need to find something that solves this differential equation. Pause the video, see if you can just spot it, just by observation, just some function that solves this differential equation. Don't try anything fancy, don't try, weird techniques, just look at it. Just look at the differential equation and see if something jumps out at you. Okay? Pause the video. 3, 2, 1. Okay, did you find it? if you thought hard enough, long enough, if you had a moment of his inspiration, something occurred to you, you may have seen this. yp equals 1. That solves the differential equation. I mean, if you take two derivatives, you get 0. So that's gone. And if you plug it in here, you get 1. 1 equals 1. Solves the differential equation. So this one we were able to find just by inspection, just by looking at it. All right? No fancy techniques needed. Now we want to find the general solution. The theorem says we need to find two complementary solutions and add them in the linear combination to this. Okay? So the next step is to look at the complementary equation. Okay? Let's see. How could we solve this one? Take a moment, see if you can find the complementary solutions here, solutions to this differential equation here. Okay, 3, 2, 1. Okay, did you find it? Just subtract y from both sides, right? If you subtract y from both sides, we're looking for a function whose second derivative is the negative of that function. It should jump out at you that, wow, wait a minute, trig functions do that, right? Sine and cosine do exactly this, right? Two derivatives of sine is negative sine, and two derivatives of cosine is negative cosine. So not only did we find a solution, but we found two, and are they independent? Is one a constant multiple of the other? One is not a constant multiple of the other, so therefore they are independent. So we have two independent complementary solutions. Independent complementary solutions. And by complementary solutions, I mean solutions to the complementary equation. Cosine, I don't know what the variable is. Let's say it's x. And y2 equals sine x. These two guys. Okay, so now we know how to write down our most general solution. The general solution, the one that will solve any initial value condition, is of the form yp plus any linear combination of these guys. C1 cosine x plus C2 sine x. There we have it. That's supposed to solve any initial value problem, so that'll solve this, right? Oops, I'm kind of can't not be in the way here. Okay, so let's solve it. Let's go to part B. That was part A. Let's go to part B. Solve this. Well, we just have to find the constants that make this true, right? So y of 0 equals 2. Okay, well, what's y of 0? So 2 equals y of 0, right? But y of 0 is also what I get when I plug 0 in here, right? Well, that makes this 1 and this 0. So 1 plus C1. Okay, and what about y prime of 0 equals 7? Okay, so 7 equals y prime of 0. What's y prime? Y prime is going to be 1 minus C1 sine x. Let's just write that down here. Oh, not 1. Sorry, when you take the derivative, that goes away, right? So you get negative C1 sine x plus C2 cosine x. When I plug in 0, what do I get? Well, this is gone. I just get C2. All right, well, I can find C1 and C2, can't I? This stuff tells me that C1 equals, just subtract 1 from both sides, 1, and C2 equals 7. Okay, so my particular solution, that solution that solves those initial value problem, is so 1 for C1, so now I'm in the way again. So I get cosine x, and C2 is 7. Right. So there we go. Okay, so in this example, we have a differential equation, linear, but not homogeneous, but it is linear, so we can try to use the techniques that we've been talking about. So we're going to try to find a general solution here. So to find the general solution, we need to find a particular solution, any particular solution, and then a pair of complementary solutions. Okay, so let's go at the complementary solutions here. If I look at this differential equation, right? Well, this is the type of differential equation that we talked. This is the type of equation that we talked about in a previous video. It has constant coefficients. If it has constant coefficients, we can look at the characteristic polynomial and get the solutions that way, right? So what's the characteristic polynomial for this? Well, there it is. Find the characteristic polynomial, factor it, find the solutions here. Oh, look, we have a repeated root, right? R equals 1, repeated. A repeated root. So when we have a repeated root, we know the solutions are e to the rx, so that's just 1x, and x times e to the 1x. And if you go ahead and check it, if you don't believe it, go ahead and check them. You'll see they do indeed solve this differential equation. Okay, so there we have our two complementary solutions. Now we need to find a particular solution. Now this looks tricky, right? I mean, there's a lot going on the right-hand side for sure. But if you think about it, all I need to do is just find anything that gives me this, all right? So I know that when I differentiate a polynomial, I get a polynomial. So one thing to try here is a polynomial solution. Let's just try that, right? So let's go ahead and do that. What degree polynomial do I need? Well, I need to end up with a second order term, and when I plug something in over here, I'm going to get the same degree that I plug in, so let's try a second order polynomial. Okay, so for yp, we're going to try this, ax squared plus bx plus c. Well, let's just see if we can get this to work. Okay, so I'm going to yeah, let's call it yp. So I'm going to have to compute its derivatives to plug them in here. Okay, so yp prime and yp double prime. Okay, let's plug that stuff in. Okay, so I need the y double prime. So it's going to be the 2a. Then we have minus 2y prime. Right? Minus 2 times this stuff. And then I have plus y. Well, that's what I'm calling, well, it's going to be plus yp, so I'm going to put that stuff in. And I need that to end up equaling this stuff, negative 3 minus x plus x squared. Okay? Let's see if we can get this to work. Well, let's go through and simplify things. So I got so let's look at the let's look at the second order terms. Okay, there's only one second order term over here. It's the ax squared. All right. So ax squared. Now let's look at the first order terms, the terms with the x next to them. I'm going to have a minus 4ax and a b x. All right, let's look at the zero order terms. I got a 2a minus 2b and a plus c. And that stuff needs to all equal this. Okay, well, if those polynomials are the same, that must mean that the a must be 1, right? Let's to get those terms matched up. So I'm done with that term. stuff in front of the x, this must all become -1, right, to get this negative x here. So negative 4a plus b has to be -1. And, oh, but I know a is 1, right? So that means that b is equal to 3. Okay, so I got my b. And then we need this thing to equal -3, right? But I know that a is a 1, so that's just a 2. B is 3, so that's -6, plus c, and that stuff all has to come out to -3, right? So c is 1. Okay, so we got it, right? We figured it out. It worked. So my particular solution is x squared plus 3x plus 1. And that will solve the differential equations. Now we have our particular, we have our two complementary, and so we can write down the most general solution, right? The general solution is the particular plus any constant times the first complementary and any other constant times the other complementary. So there we have it. Usually I write y equals, but I just didn't fit it in there this time, right? And this will solve that differential equation. Now we were also asked to find the solution to the initial value problem. Right? Y of 0 equals -2, y prime of 0 equals -1. Okay, let's go ahead and do that. So, oh boy, running out of space here. Oh boy. Okay. Y of 0 equals -2. All right, so -2 equals y of 0. But y of 0 is what I get when I plug 0 in here. So that's, most of this stuff is gone, right? I mean, it's just, I just get 1 plus c1. Well, that's nice. And then y prime of 0, on the one hand, we were told it equals -1. But on the other hand, I can compute y prime, right, from this stuff. It's going to be 2x plus 3 plus c1 e to the x plus c2 e to the x plus c2x e to the x. Right? But when I plug 0 in here, that's gone and that's gone. I get 3 plus c1 plus c2. Right? Okay, so the first equation tells me that c1 is equal to -3. Plug it into the other one, I see that c2 has to equal -1. And so there is my solution to the initial value problem. Y equals there we have it. Pretty snazzy if you ask me. All right, so I think that's it for this video. Hope you learned something, and I'll catch you on the next one.